So today we're going to be learning about minerals and rocks. If you look at the two pictures here on the title screen, one of them is minerals, which is this one here. These are all different types of minerals, and this one is rocks. And we're going to talk about how those are similar to each other and how they are different. So how are minerals and rocks different? Minerals have to have 4 characteristics, and these 4 characteristics have to be true in order for something to be classified as a mineral. The first one is it has to be formed by a natural process, on or inside the earth. So for instance, evaporation of water, cooling of magma are different things that happen that are natural processes that happen either inside the earth or on the earth's surface. They have to be inorganic, which means they're not made by a living thing or come from a living thing. They also typically do not contain carbon, although this one doesn't always hold true for everything. A mineral is also either an element, such as what you see on a periodic table, sulfur, sodium, or a compound, like salt, NaCl. Minerals are also crystalline solids. What that means is that it has a definite shape and volume. So only solids can be minerals. You can't have liquids as minerals, but not all solids are minerals. Now when you have rocks, rocks are different because they're mixtures of things. So they're mixtures of minerals, fossils, and even some organic material. Rocks can be made from living things or things that were once living. A similarity between rocks and minerals is that they're both formed by processes within or outside of the Earth's surface. So now we're going to spend some time and talk just about minerals. So there are 90 elements that occur naturally in the Earth's crust. These elements bond together in a variety of ways to create all the minerals that make up our lithosphere. Most of the minerals that we have are actually made up of 8 elements, and then trace amounts of other elements. Because notice it's 98%, so there's still 2% by weight of other elements in the Earth's crust. But the majority of the Earth's crust is made up of oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. When we look at oxygen and silicon, these make up the biggest percentage together of the elements in the Earth's crust. They also make the biggest group of minerals, which are known as silicates. So minerals can either be pure elements, like sulfur, or they can be compounds. So 2 elements bond together to form a compound, such as halite, which is NaCl. Okay, so we just talked about identifying minerals and the tests that we use to identify the minerals. I'm going to actually run through these with you guys in kind of live action. So the first one we just talked about was color, the general appearance of the mineral. So when you have your unknowns, you basically just look at what do they look like. Like this one's white, and you're like, okay, that's great. This one's kind of a silvery gray color. This one's green, that's helpful. Maybe a browny purpley color. This one's clear. Okay, that might be important. And this one almost has like a pearly sheen to it. Okay, so we have those down. Then the next one was hardness. So hardness is how easily a mineral can be scratched or can scratch something else. For the lab that we're going to do, we're going to be looking at our fingernail and a glass plate. So the first thing you do is you figure out to see if you can break the mineral down with your fingernail. Or does your nail get filed? So if your nail gets filed, then the mineral's harder than your fingernail. If you can break down the mineral, then the mineral's softer than your fingernail. For instance, I know off the bat that this one is softer than my fingernail. Scrape the mineral, it actually looks like it begins to snow. And there's a whole bunch of white powder that comes off right in this area here. Okay, so this one would be softer than my fingernail. Do the same thing with the green one, and that's harder than my fingernail. And I go with this one, I'm like, oh, all right, well that one's definitely softer than my fingernail because it's just flaking right off. And then this one, okay, so this one is harder than my fingernail. And then this one is harder than my fingernail. So now we look at, is it harder than glass? So here's a nice fresh glass plate that has no scratches in it. We're going to run through to see if any of them are harder than glass. Well, this one I know is softer than my fingernail, so I'm going to put it off to the side, as is this one. We're done with those. So now we're kind of left with 4. And I'm going to start with this one, the green one, and you try and scratch the glass, and the glass doesn't scratch. So it's softer than glass. So the hardness would be between your fingernail and glass. Then we take the silvery one, and oh, look at that, leaves a big gouge in the glass. So this one will be harder than glass. See, you can see the big gouge in that. So that would be how you would test for hardness. The next one that we looked at is luster. So is it metallic or non-metallic? Well, metals kind of shine a certain way. There's a lot of things that reflect light that aren't metals, like toilet paper dispensers and water bottles and glass and all sorts of things. When you're looking to see if it's metallic or non-metallic, you're looking to see if it reflects light like a metal. So think of like a chrome bumper or a penny, that kind of thing. So when we look at these, we're like, all right, well, that one kind of looks like plastic. So that, although it reflects light, doesn't reflect light like a metal. You can't see through a metal. Same thing with that one. So those are definitely non-metallic. This one's kind of pearly. Definitely doesn't look like a metal. So that's non-metallic. This one and this one are a little bit more challenging because this one's really shiny. So is this one. But this one's really, really light. This one's really dense. Metallics tend to be a lot more dense because they're made of iron. There's usually a lot of iron in metallic minerals. So this one's non-metallic, even though it's really shiny, but it's non-metallic. Now these two are both dark, but this one is also really light. And the densities you'll see between these two minerals next class. But this one almost has more like a glassy look to it versus this one. So I pulled a couple other metallic minerals that we haven't really been using for this demonstration to give you an idea of other metallic minerals. So this one is really gold in color, definitely more dense, heavier like a metal. So is this one. Although this one's not as shiny, density is going to be a really strong thing to clue you in if it is a metal or not. Because all of your metals are very, very heavy, whereas a lot of your non-metals are really light. Now another test is streak. So streak is kind of the powdered form of a mineral. So for that we need our 2 streak plates. We have a black one and a white one because the powdered form of a mineral can either be really light or really dark. So for instance, I'm going to start with my white mineral here. I'm going to bring all my minerals back over. I'll even bring some of my new metal ones over. And then my mica. So here I have my white mineral. And when I rub that on the black streak plate, you can see that it's a white streak. This one is really cool because it actually streaks like a dark gray. So it's a very silvery gray in its powdered form. So in order for it to streak on the plate, it has to be softer than the streak plate. So there's some of them that won't streak on here because they're harder than glass. So for instance, remember my glass plate? There were some that scratched it. If it scratches the glass, it means it's harder than glass. Streak plates also have a hardness. If it's harder than the streak plate, it won't come off on the streak plate. It'll actually scratch the streak plate. So for instance, if I take this one, which scratched the glass, and I try and do it on the streak plate, it's actually leaving a gouge in the streak plate. So it actually doesn't scratch the streak plate. One of the last ones is cleavage and fracture. For this, you don't really need any equipment. You just have to look at the mineral and observe it. So for cleavage and fracture, it's how a mineral breaks. Does it break smooth and flat, or does it kind of break jagged? So if we were to organize these into, I'm going to move these one, into which ones have cleavage and which ones have fracture, well, we look at which ones break in kind of a uniform pattern. Well, this one peels. So this one's considered to have cleavage. This one, if I was to slam it on the ground, it would still break along these lines. They would just get smaller. So this one has cleavage. These 4, oh, this one does too. This one actually has cubic cleavage. It's a little bit hard to see on this particular mineral, but it's a little bit more smooth. These ones here have fracture. There's really no rhyme or reason to their breaking pattern. So that's kind of very generic, very easy way to figure out if you have cleavage or fracture. One of the last ones is magnetism and refraction. So those are kind of some specific characteristics to certain minerals. So when we talk about double refraction, it's only really one mineral that actually will give double refraction, which is a double image. And that's kind of these see-through ones. So you actually have to find, if you have a see-through mineral, you can check for this. So I'm going to pull your lab or your PowerPoint, and for double refraction, you simply put it over some type, and then you look at it, and you should see that it gives a double image. So that is an example of double refraction. You can also have a mineral that is magnetic. So we pull some of our minerals out, like, well, in order to be a magnetic, it probably has to be a metallic mineral, because iron's what's magnetic. And you just take a magnet and you put it on the mineral. You're like, nope, that's not magnetic. That's not magnetic. That one is magnetic. So that's a really unique property to this particular mineral, that it's magnetic. So those are some of the key identifying terms that you're going to need to know for your lab tomorrow on minerals. So now we're going to move from minerals and into rocks. These are the key points about the three types of rocks that we have on Earth. We have igneous, sedimentary, and metamorphic. Well, igneous is the most common type of rock. It's formed from the hardening of molten material, whether that be on or inside the Earth. And it's often identified based on its crystals and its color. So you have two identifying factors. Igneous rocks are identified by two factors: composition and crystal size, or location of formation. Sedimentary rocks are the second most common type of rock, and they're made up of sediments, such as loose materials like rock fragments, mineral grains, and possibly organic materials that have been moved by the agents of erosion, which is wind, water, gravity, or ice. When these sediments are pressed and cemented together, or when the minerals form from solution, they make up a sedimentary rock. They're often identified based on their sediment layers, but they don't all contain layers. And they make up about 75% of all rocks exposed on Earth's surface. Metamorphic rocks are the least common type of rock, and these form because of temperature changes and pressure changes, usually at converging plate boundaries. Metamorphic rocks can form from sedimentary, igneous, or other metamorphic rocks. And the changes can be both in the form of the rock and the composition of the rock, or both. And they're typically identified based on the flattening of mineral grains. So now we're going to look at each of these individually. So tomorrow in your lab, you're going to be looking at classifying different types of igneous rocks. The first thing you're going to look at is color, and that's really the composition of the rock. What's it made up of? The second thing you're going to look at is the location. Where does the rock form? So these two pieces give you kind of an identification of different rocks. For instance, when you look at composition, you're going to be looking at color. Is it dark and dense? Is it moderate color? Or is it light in color? If it's dark in color, that's known to be mafic or basaltic. Those two terms are interchangeable. And these rocks contain a lot of iron and magnesium and very little silica. So they're very dark in color and they're very dense. Intermediate rocks, or andesitic rocks, contain equal amounts of iron and magnesium and silica. They're a moderate color and density. And then lastly, you have felsic granitic rocks. These are very little iron and magnesium and lots of silica. So they tend to be light in color and low density. Location is going to be the second thing you look at. Where do you think the rock formed? Well, if it's intrusive, it formed inside the earth. So when you have an intrusive rock, you have visible mineral grains. So you see different colors in an intrusive rock because there's different minerals. Extrusive rocks that form on the Earth's surface. So they cool very quickly. The lava cools on the Earth's surface very quickly, so they all tend to be uniform in color. So if we look at these pictures over here, we can see, if we follow this intrusive column down, that there are different colors that we can visualize within each rock. Like I can see dark and I can see light colors in all of them. So those would be intrusive rocks as a category. These ones all look very uniform as one color. They form very quickly. There's not a lot of different colors in them. So those would be all extrusive. Then we can also look at composition. Mafic rocks are dark. Intermediate rocks are kind of a moderate color. And then felsic rocks are a lighter color. So the next type of rock is sedimentary rocks. And when we classify sedimentary rocks, they fall into three categories. The most common sedimentary rock is detrital, which means it's made from other rocks. It's basically loose sediments that have been pushed together from pressure from above to form rocks. And they have a granular texture, which is named based upon the sediment size. So it can range from above 2 millimeters all the way to as small as 0.004 millimeters. So when you look at a detrital rock, you're just trying to see, does it have a grainy texture or can you see pebbles in it? Will give you a good idea of a detrital rock. Chemical and organic rocks are harder to tell apart, but chemical rocks form when dissolved minerals come out of solution, and they're typically found in areas where water was once prominent and often contain the calcite mineral. And then finally, organic are made from the remains of once living things. When the plants or animals die, their bodies, they're buried and then compacted and cemented together. The last type of rock that we classify is metamorphic rocks. And we're basically looking at metamorphic rocks as if they're foliated or non-foliated. And that just means, are they in layers? Are they in parallel layers kind of squished together or not? So foliated rocks are when all the mineral grains flatten in parallel layers. And the layers form perpendicular to the direction of pressure. The minerals are pressed so tightly together that they become waterproof, that water can't pass through them. They're impermeable. Non-foliated rocks, layering does not occur. These ones are caused by hot liquids that flow around the rock that changes the crystal structure and or the composition. So the last thing we're going to talk about is the rock cycle and how rocks change from one type to another. And there's lots of different ways that rocks can go from metamorphic rocks to igneous rocks to sedimentary. But if you look at the diagram, I would say most rocks are born, if you will, as igneous rocks. So when they're born of igneous rocks, they go through solidification, so to be from magma. From there, they can either go under weather and erosion to become a sedimentary rock, or under heat and pressure to become a metamorphic rock. Metamorphic rocks, in turn, can melt back into magma or break down to sediments to form sedimentary rocks. So in the rock cycle, just in the water cycle, nothing ever really leaves the rock cycle, it just changes form. Now you guys should make sure that your notes are complete. There is a lot of vocabulary in this PowerPoint. And also do the WISC questions at the bottom of the form. And I'll see you guys tomorrow.